All right. In this lesson, we're going to be describing vascular of cardiovascular physiology. And what I don't want to do is I don't want to overcomplicate any of this uh, any of this effort here. So the vascular system is comprised of the arteries which take blood away from the heart and the veins which return them back. The pulmonary artery, which leaves the right ventricle, is an artery with deoxygenated blood, and the pulmonary vein has oxygenated blood. Otherwise, you usually consider most of the arteries to be carrying the oxygenated blood to the body. The purpose of moving the blood and plasma through the body is the purpose of moving nutrients and oxygen and carbon dioxide around the body as needed. The aorta, as we come down in size, so think about aorta down to arteries, right? Brachial, radial, et cetera, eventually get down to arterioles. And what I have here is really an average pressure seen at aorta, artery, arterial. There's a dramatic drop from the beginning of the arterial down to the capillary system, and then you continue that drop as you're going all the way up. There are valves in the veins which prevent backward flow because of the lack of some of the elasticity and recoil that occurs in the larger arteries from smooth muscle. There can be some over here, but generally there are endothelial cells that line all of the vessels, and there's a greater amount of smooth muscle that occurs in the aorta and the larger vessels as you're coming back here, because blood pressure is essentially the mechanism of the heart squeezing this bolus, this wave of blood out, and it is the recoil or that counterforce of the vessel wall that generates the pressure, which we call blood pressure. And if you can imagine the heart, brain, GI system, gastrointestinal system, kidneys, muscle, skin, they all need nutrients to survive, but it is a very complicated system to maintain homeostasis as is appropriate. And so it is this smooth muscle that exists in the arterial supply that is regulated to maintain good flow as appropriate. For example, if you see a ghost and you faint, it's because you have less blood here. You may be ashen white because you've constricted down because your body's in fight or flight and preparing your muscles to run away. The control of this, if you release like adrenaline, is going to apply everywhere. However, there's a sympathetic nervous system that innervates the vessels as well as parasympathetic. Sympathetic is fight or flight, and so it can help to manage the constriction of the vessels. A key component of the vascular system is that the lungs, the RV and LV, pump the same amount of blood and are in series here. So that however much is going on here is the same as going here. An example of that is when I take a cross section of the pulmonary artery and aorta, and you can see the equal flow here, or they are equal 7.1, 7.2. And same thing if I look at the cardiac output from a left ventricle and right ventricle, they're going to be about the same. If they are not, just for fun, 6.1 versus 7.9, we have to ask ourselves, what could that scenario be a result of? And that helps us, for example, in this case of tricuspid regurgitation, which you're going to see on this cine loop here. You can begin to see that regurgitant volume shooting up through the tricuspid valve. And so when this right ventricle squeezes, it's got backward flow, which explains why the right ventricle is squeezing more. But in most states, they're going to be equal. So next section, we're going to be discussing blood pressure and the resistance that occurs in the vessels. So now let's discuss blood pressure. And as before, blood pressure is the pressure in millimeters of mercury that is the result of the cardiac output pushing against the vessel wall and the vessel wall recoiling back. And so just to provide a few different pieces, blood pressure is a result of cardiac output, which is related to stroke volume and heart rate, times systemic vascular resistance, which is a result of diameter, length, viscosity, which we're going to get into next. So let's first start with systole and diastole. So when the heart squeezes together, we have systole. So for example, in this, we can see a right ventricle. The squeezing action is systole. The relaxation is diastole. And so we have a systolic blood pressure and a diastolic blood pressure. These are normals. If you say 120/80 as normal, that's a pretty good place to start, and anything below that is going to be a good target. Once you get 90/60, then you're worried about having enough to perfuse. And the pulse pressure is systolic blood pressure minus diastolic blood pressure. So an example of, well, this is a pulmonary artery here. If you imagine what the systolic pressure is minus the diastolic pressure, we have regurgitation here from a bad pulmonary valve. And so in this scenario, you can see this is all the forward flow, but we have this reversal of flow. The result is the pulse pressure is increased, as opposed to a standard where you don't have that regurgitation. So you have a wider pulse pressure as a result of anything where the diastolic blood pressure isn't being caught by that recoil of the closed valves in the arterial system. The mean arterial pressure you would think would be systolic plus diastolic divided by 2. However, this is not correct. I have these sort of representing multiple flows here, and the majority of the time, the body is in a diastolic state. So that means you're wanting a mean pressure is going to be reflective of 1 systole plus 2 diastole. You can get there multiple divided by 3. You can get there different ways. For example, 1/3 pulse pressure plus diastolic blood pressure. If I assume a normal pressure of 120/80, then you can see how we get to these numbers here. So let's talk about a blood pressure cuff and how we acquire this information. So if I put a cuff around my arm here, and I've got my artery, which is wide open while it's in a relaxed state, deflated. As soon as I inflate the cuff, what's going to occur is that artery is going to flatten out, and the vein's always flat. But what's going to occur is as the pressure exceeds the systolic blood pressure, it's going to collapse that vessel, and it's not going to let it open. As I start to release the pressure, and I'm listening with a stethoscope right here on the arm in the sort of the brachial fossa there, I'm going to hear that vessel barely open and snap shut, and I'm going to hear that faint noise. That's going to be whatever the millimeters of mercury I see is going to represent the systolic blood pressure. And then in the middle, like right around 100 in this example, I'm going to hear it clapping, because that is going to be where the pressure in the cuff is allowing for it to open up maximally and close the most. As I begin to release down to the diastolic blood pressure, it's going to begin to barely close, and that last noise I hear is going to be the diastolic blood pressure. And so that's how we can get to the blood pressure using a cuff. One of the things that I like to also show an example of is if you consider the circulatory system and how pressure is equalized. If I take the flow from aorta here, descending aorta here, and SVC, which is the flow back to the heart, they should all equal the same amount because it is a closed loop system. And in fact, if you take ascending aorta here minus descending minus SVC, you'll see that ascending equals the SVC and descending. So thank you.